Good morning, everybody. Welcome to Natural Science, Grade 8. Today we're going to be discussing magnetic effects. Before I start, remember ground rules, all cameras off, and we're only going to chat about content for today. So magnets are very interesting and really good information for us to know about how things work. So I'm going to talk about that today. So by the end of this lesson, you're going to know more about the magnetic effect around a conductor and how you can make an electromagnet, which would be quite an interesting experiment for you to do. Okay, to recap on yesterday's lesson, we learned that a fuse acts as a device to break a circuit in the case of an fault or an overload of the circuit. Now, fuses is an electrical device which is used in order to protect the system of the equipment from overcurrent. And the fuses blow open, it will open the entire circuit and it will stop the current. So basically, we learned that fuses are there to protect you. It serves, it breaks the circuit when there's an overcurrent and it stops the current from flowing. And we also discussed electromagnetism. So the electric-magnetic force are one of the forces of nature, and it includes an electric force which pushes all charged particles, and it also has a magnetic force which also pushes moving particles. So basically, electromagnetism is about electricity and magnetism working together to create an electromagnet. So yesterday somebody asked me about permanent and temporary magnets. So a permanent magnet is a magnet like we saw yesterday, that solid bar graph, that solid bar. Now that solid bar was because it is solid, it's a permanent magnet because the arrangement of the atoms are fixed. Okay, so that's what makes it permanent. Now, like and examples of these are iron, nickel, cobalt, and some alloys of rare earth materials that occur naturally, such as idle stone. Then also we have a temporary magnet. Now a temporary magnet is basically like an electromagnet, because when you apply electricity to it or an electric current to it, then the atoms start moving in a specific direction. It flows in a specific direction. So that's what is a temporary magnet. It's basically an electromagnet. So they act like a magnet in the presence of a magnetic field, but it loses its magnetism when it's not in a magnetic field. And when and then we get electromagnets. These wound coils of wire, they function as magnets with an electric current that is passed through it. And you can adjust the strength and the direction of the current. So the strength of the magnet can also be altered. Often the coil is wrapped around a core of soft ferromagnetic materials around a steel. Now you could ask yourself, what is ferromagnetism? So basically, it's a form of a magnet that is attracted to magnets, okay, to other magnets. It has a magnetic field around it. Now, an electromagnet, if we look here in this picture on the right-hand side, so an electromagnet is a temporary magnet which produces a magnetic field only when the current passes through the coil of a conductor. So if they ask you in an exam, what is an electromagnet? So you're going to basically give this answer. You're going to say it's a temporary magnet that produces a magnetic field only when a current passes through the coil or a conductor. So, and a simple experiment to understand the magnetism of an electromagnet is to connect a solenoid to a battery, to show, as shown in this diagram in the bottom. So it basically shows that when the current passes, then a magnetic effect is induced and it makes it magnetic. So we're going to move on to the next slide, and we're going to discuss a magnetic effect around a conductor. So um, let's see. A current causes a magnetic field. So we know that when a current passes through, it causes a magnetic field, such as an electromagnet. And an electric current can be used for making temporary magnets. So no, you must understand this, that the electric current makes the magnet temporary. So it becomes an electromagnet. And the moving charges, which is the current in the conductor, such as the wire, it causes a magnetic field around it. So the moving charge in the conductor, it causes the magnetic field around it. So who knows, why does an electric current produce a magnetic effect? Does anybody know? Okay, so I'll tell you. So the current is a flow of electrons, and electrons is itself a tiny magnet. So this is something new that you've learned. You're going to say that electron itself is a tiny magnet. Remember that in matter and materials, I told you that electrons move in harmony with the protons, and this is because it has a magnetic effect on it. So they are attracted to the protons because of the magnetism that they carry. So the current flows to the electrons, and the electron is a tiny magnet. When a charged particle, such as an electron, is in motion, the magnetic lines of force rotate around the particle. So basically what that means is when a particle is charged, so the electrons move in motion and they rotate around the particle. Since electric currents move through a wire consist of electrons in motion, there is a magnetic field around the wire. So now since this current is passing through it, it means that there is electrons are moving and it creates a magnetic field around the wire. So let's look at the picture to explain this. So basically, this is your proton and this is a neutron and it's in your nucleus. And then you have the electrons flowing in its orbit around each, you can either call it a sphere or each shell. Okay, so now these electrons are orbiting around it, and as they're moving in harmony. So remember we said that opposite charges attract each other. So the electron was a negative charge and the proton was a positive charge. So these are moving in harmony with the proton, and it's attracted because it has certain magnetic force to it. So as this proton like rotates around, sorry about that, we have this electron moving around. So it's actually it spins around the orbit and they move in harmony with each other. So the magnetic field and how it is created. So let me explain that. A magnetic field describes a volume of space where there is a change in energy. So basically you have the space, right? And it's caused because the energy levels change, so that there is a change in energy. So you will see a simple way to detect a magnetic field with a compass. Now, Ampere suggested a magnetic field is produced whenever an electric charge is in motion. So basically, what that means is a field is created when electrical charges move. Okay, in motion means that it moves around. So the spinning and the orbit of the nucleus of an atom produces a magnetic field, as does the electric current flowing through it. So basically, the spinning of the orbit has magnetic fields around it in the atoms, and then the current is flowing through it through the wire. Both of them work in harmony together, and it causes an electromagnet. Now, the direction of the spin and orbit determines the direction of the magnetic field. So, if the current is flowing in one direction, so it will determine the direction of where the magnetic field is. And this strength is now called a magnetic moment. So the strength of the field is called a magnetic moment. So the motion of an electric charge produces a magnetic field, and it is an essential concept in understanding magnetism. So you need to understand that when the electrical charge, the movement of this charge, and the movement of how the electrons move um, together, this is essential in understanding it's magnetism. It's very important that you understand that they both move in harmony to create the magnetic field. And the way in the direction it moves, it basically tells you that that is the direction of the magnetic field. A magnetic moment of an atom can be the result of the electron spin. So you saw basically in the picture below, in the previous slide, that the electrons were spinning in an orbit. So this is the magnetic moment, which is an electronical orbital motion, and a change in the orbit motion of the electrons is caused by an applied magnetic material. So magnetic field. So what this means is that, I'm going to repeat myself, the electrons are spinning in its orbit. And as it is spinning in its orbit, it moves in a particular field. And this is caused an electron orbital motion. So don't worry too much about all these fancy words. The only thing that you need to understand is that the electrons move in harmony with the protons, and this causes a magnetic field. And then you need to know that the electrical flow flows through the wire, and both will move in a certain direction. And as they move in this particular direction, it determines the direction of the magnetic field. So that's the most important thing that you need to know in this slide here. And since all matter is made up of atoms and all atoms have electrons, then there is motion. So all atoms have magnetic fields. So does anybody want to take a try and explain what I just said? You can raise your hand and I'll give you a chance. Okay, no problem, I'll continue. So the answer, the question that I'm asking you is, all atoms have electrons that are in motion. Now, do all the atoms have magnetic fields? So this is a good question to ask. Do all atoms have magnetic fields? So the answer is actually basically yes and no. And the reason would be because all electrons do produce a magnetic field as they spin and orbit the nucleus. However, in some atoms, two electrons spin and orbit in opposite direction pairs, and the net magnetic movement of the atom would be zero. So basically, let's take this as an example here on the right-hand side. So we have our electrons here. There's two electrons and then there's two protons, and they are spinning in opposite directions. So this one atom here is spinning going anti-clockwise, and this electron here is going clockwise. So they're spinning in opposite direction. Now, because they're spinning in an opposite direction, it basically means that they cancel the magnetic charges around it. So the opposite direction effect cancels the magnetic charges. So they say they have a net magnetic moment of an atom is 0. So that means that now this atom is not it doesn't have a magnetic charge because it's moving in an opposite direction. And this is different from an electromagnet where they all move in the same direction, and that causes magnetism. But when the electrons move in opposite directions, they cancel each other, and then that atom would not be magnetic. So remember that the direction of the spin and the orbit of the electron determines the direction of the magnetic field. So basically, the direction of the spin determines the direction of the magnetic field. And now we're going to talk about electron pairing. So electron pairing refers to the atoms in most material. So in the experiment that we did here on the side, that shows you that the two electrons are spinning and orbiting around the protons and the neutrons in the nucleus. The electrons are basically paired. And this means that they spin in an orbit in opposite directions. So as I said that this one electron is moving in an anti-clockwise and the other electron is moving clockwise, and they spin in opposite directions. So since these magnetic fields produced by the motion of the electrons are in opposite directions, they basically add up to 0. Okay, so if they add up to 0, it means that now this atom doesn't have magnetism. And the overall magnetic strength of the atom of all paired electrons is 0. So when it is 0, it is called a diatomic magnet. Okay, so the information that I'm going to give you now that explains what magnetic materials are is a little bit intense for you to understand, but don't worry too much about it. The most important thing that you need to know is that when the electrons pair in the atoms, they basically have no net magnetic movement. So that means that the magnetic movement means it is 0. It cancels each other because it's moving in opposite directions. But there are some exceptions. So when placed in a magnetic field of a magnet, diamagnetic materials will produce a slight magnetic field. And this opposes the main magnet. Okay, so now when you place this diamagnetic material, for example, this atom that has no magnetic charge in a magnetic field. So basically what happens is, you know how you have a light, it basically opposes the main magnetic field. So both ends of the bar magnet will repel a diamagnetic material. So that means they don't attract each other, they repel each other. In a diamagnetic material is placed in a strong external magnetic field, and the magnetic field strength inside the material will be less than the magnetic strength surrounding the material. So basically, the magnetic field inside the material will be less than the magnetic strength in the air surrounding the material. So most important for you to know is the strength inside the material will be less, and the magnetic field strength in the air surrounding with the material will be more. So the slight decrease in the field strength is the result of the realignment in the orbit of the motion of the electrons. So this means that because there's a change in in the movement of the electrons, there's a decrease in the field of strength. So we have diamagnetic materials. Basically, examples of it are zinc, gold, mercury, and bismuth. So in the test, if they ask you, give an example of a diamagnetic material or give two examples. So the easiest for you to say is either zinc or gold, or gold or mercury. Bismuth will be a little bit difficult for you to remember. But if you do remember it, then that's very good. Another key concept in magnetism is that diamagnetic materials will oppose an applied magnetic field. So when we say that it opposes an applied magnetic field, we basically mean that it repels each other. And both ends of the magnet um, will repel the diamagnetic material. So in the next slide, I'm going to teach you or do an experiment. And through this experiment, we're going to just decide if there's a field around, if there's an electric field around a conductor. So basically, that's any wire around you. You want to decide if there is an electrical field, or sorry, not electrical field, magnetic field around the wire. So you can do this experiment, and you can construct a circuit which contains a battery, copper wires, and a switch. So it's a very simple circuit that you're going to construct where you just need batteries, copper wires, and the switch. You don't need a light bulb here. By putting the plotting compasses on either side of the conducting wire, as shown in the diagram, you will you can see here in this diagram, they put compasses here, and they have the wire that is conducted to a switch and a battery going through the compass. Now keep the switch open. Now what would you notice about the needles of the plotting compass? Does anybody want to answer? If the switch is open, that means electric current is still not passing through. What happens to the needles on this compass? Levi? Morning, Levi.
Morning, ma'am.
How are you?
Fine, thanks. And how are you?
I'm good, thanks. You know the
Uh,
answer.
about what happened to the needles? The needles are not moving.
Yes, the needles are not moving. We can see it's all pointing to one direction. Very good.
Thank you.
Okay, thank you so much for that answer. So the
Pleasure.
needles, you're welcome. So the needles should point to the magnetic north. So the needles do not move, they all move in the same direction, and it's moving in the direction of the magnetic north. So remember that in a magnet you have the north pole and the south pole. So naturally it will just go and point to the north. Now let's say that we're going to close the switch. And if we close the switch, what will happen to the needles of the compass? Does anyone want to try? Yes, Levi?
If the switch is closed, then they'll move in different directions
Why?
because the because you see the needles. The needles are the indicators. If the needles is the indicator which shows that if there's a magnetic field, yeah.
Okay, very good. Well done. So if you close the switch, let's see what will happen. Levi is absolutely correct. Okay, so the needles of the compass will move. And now the needles of this compass will move because when we close the switch, an electric current is going through the wire. So, but this shows you that there is a magnetic field around the wire. Okay, so what does this pattern of the compass tells us? And I answered your question, but does anybody want to tell me what would happen if the pattern of the compass? What does the pattern of the compass tells us? Here's a picture here. Can you see that the needles are all moving in different directions? Okay, so this tells us that there is a magnetic field around the wire. So here in the top direction where it's number 2, this this circuit was open. There was no current going through it. So when there was no current going through it, all the um, needles on the compass pointed to the magnetic north. But the moment we closed the switch and we applied an electric current through it, then these needles went in different directions. And because it moves in different directions, it gives us, it tells us something. And it basically tells us that there is a magnetic field around the wire. Okay. So we saw that by plotting compass reacts to magnetic fields. The plotting compass changed the direction when the current was switched on. So you saw in the picture that all the needles moved in different directions. And this was an indication that the magnetic field moved, there is a magnetic field around the wire. So um, was there a current when the switch was off? No, there was no current because the circuit was open. So this means that the presence of electric current in the wire must have produced a magnetic field. So I want you to remember this here very clearly, that through this experiment we learned that the presence of an electric current in the wire basically produced a magnet. And that is how an electromagnet is made, through a simple switch. Now you can try this at home, and I'll give you where you can test if you have a compass and if you can make a simple circuit with just a switch wire and a battery, and then you can test to see if the needles of the compass moves. And then your experiment would be proven that the presence of an electric current in the wire produces a magnetic field. Okay, any questions with that section? With the no. Okay, so we're going to discuss electromagnets. So let's look at this, Levi.
Yes, there is. I still have one. Uh,
Okay,
remember that circuit that we did the circuit about the magnetic field and all that.
yes.
It also must need a light. It also should need a light bulb because that will tell. Yeah.
Yes, you can put a light bulb because it will tell you. That's very clever, Levi. Well done for thinking of it. Because in
Thank
yesterday's experiment, well done. In yesterday's experiment,
thank you.
we did we put a light bulb there, and
Yeah.
to show that there was electricity in the wire. So the fact that the light bulb lighted up means that you know for a fact that the electric current is flowing, because sometimes it could be faulty, that the wire is faulty, it won't know. So if you do put a light bulb, it will show you that the current is passing, and then you can put the uh, uh, a compass next to the wire, and if the compass, you'll see that the compass moves. Well
Okay.
done, Levi, for being so for listening very, very well. And you make me
Thank
feel
you.
happy now, because
Thank
I
you.
know that you're welcome, because I know I've taught you something. So electromagnets can be used in all sorts of practical applications, like for example in a speaker, electric bells, as you see in this photograph here. Okay, so we basically use electromagnets in all sorts of applications, and that's you using it in everyday life. An electromagnet is a type of magnet in which the magnetic field is produced by an electric current. Okay, so important for you to know is that an electromagnet is a type of magnet which is in which the magnetic field is produced by an electric current. Now, electromagnets consist of wire wound in a coil. Okay, we have electromagnets. It consists of wire wound in this coil. So if you look at this picture here, you can see this wire here, and this wire is wound. That means it's wrapped in a coil. So now who knows why this wire is wrapped in a coil? I did explain it's one of the properties of, um, uh, I told you there were four um, elements that basically improved electricity. And one was, if you remember, you can use the example of the wool and the finger. Can you remember? It was length. Okay, so the wire is wrapped around the coil here to increase the length. Now, if you increase the length of the wire, it allows more electricity to pass through. So that's why we had wire passing through it. So an electromagnet usually consists of wire wound in a coil. And the longer the piece of wire, the greater the current that is going to go through it. And a current through the wire creates a magnetic field. So the current through the wire, it creates a magnetic field, which is concentrated in the hole. Okay, and it denotes the center of the coil. Okay, so we know that this current in the wire, it creates a magnetic field, and it is in the center of the coil. So it's concentrated mostly in the magnetic field in the center. Okay, so let's say you can do this experiment at home where you are going to make an electromagnet. So what you would need is, you can copy this down. I'll leave it on for you for a few for a minute or two. You're going to need one iron nail, which is approximately 15 centimeters long. So can you see here in the picture at the bottom, you have an iron nail. Okay, and then you'll need 3 meters of insulated copper wire. So this is copper wire that's wound around this nail, and you'll need 3 meters of it. Okay, and then you'll need 2 D-cell batteries. So you can use 2 you have different strengths of batteries. You have A, triple A. So for this experiment, you'll need 2 D-cell batteries. And then you'll need a metal paper clip. Okay, because metal is a good conductor of electricity. And now you'll need iron fillings, but then you'll have to buy the iron fillings to do this experiment. And then, or what you can do is, if you don't have iron fillings, you can put um, little pieces of any iron around you, or your paper clips near around this, and then you can make your circuit. Okay, so instructions for doing this: you're going to wrap the insulated copper wire tightly around the nail. So can you see that we started here, and then we wrapped it around this nail? Okay, and it goes up. And then you're going to make sure that you wrap the wire in the same direction. So you can't wrap it in one direction and then move to a opposite direction. Levi, you have a question?
Ma'am, I've been reading in my natural science textbook. When you were talking about the electromagnet, I was about to tell you the one of the most interesting features of it, because like when the electric current is turned off, the magnetism is also turned off.
Yes, very good. Well done for that. So,
Yeah,
well done, good boy.
thank you.
So when the current is switched off, you must know that there's no magnetism around it. And then all, like in the previous picture that we showed you, all the needles point to the magnetic north. It points all in one direction. And then the moment we added electric current through it, all those needles went in different directions, which basically showed you that there is current around it. Now, back to, well done, Levi. So back to our instructions. We're going to strip some of the insulation off at the end of the insulated copper wire. So basically what this means, you can, if you can ask mom or dad to help you. So at the end of the copper wire, it's just, you won't be able to see the copper wire inside. So you're going to very carefully take a scissors, and you can't cut quickly now. You have to cut very slowly. You're going to cut a small piece of the rubber around the wire. Just not a big piece, just a small piece, and you're going to go slowly, because if you cut it too fast, then you're going to cut the wire out as well. And then when you cut it slowly, that means you find that the rubber part's going to get loose. So when the rubber part gets loose, you'll find the exposed copper wire. Now you're going to do this before you put your switch on, hey? You're going to do this before you connect anything. And then you're going to take that wire piece that comes, that is free now, the copper wire inside, and you're going to turn it around. You're going to, you know, like how when you take paper and you twist it, so you're going to twist that copper wire around. And by you doing that, you're actually making it stronger. You're strengthening the copper wire in the sense that you are, because you want to attach it to something now. So you have to make it stronger, because all of it are separate and they're very, very thin. Now when you twist it, it binds together. Then you're going to attach the ends of the insulated copper wire to a terminal of the battery. So basically what you're going to do is you're going to take that copper wire after you twist it, and you're going to attach it to the battery. And then you can use masking tape or insulation tape to hold it together. Okay. And then you're going to hold the wrapped nail above the paper clips. Then you're going to disconnect the wire from the battery and hold the wrapped nail above the paper clips. And if first you're going to try, then you're going to put your paper clips to make a switch, and then instead of disconnecting the battery now, you can make a switch. So when you close the switch, you will have iron fillings and place them on the paper. So when you close the switch, you'll notice a pattern like this. Can you look at the picture on the left-hand side? You'll see that the iron fillings move around in a pattern. So they move in a circular circle pattern here, and towards the North Pole and the South Pole, they move outwards. They spread outwards. Okay. So you have homework. Your homework is that you can make an electromagnet. But if you can't make an electromagnet, for example, if you don't have iron fillings, or if you don't have paper clips, or you don't have 3 meters of copper wire to play around with, then you can watch this YouTube video, how to make an electromagnet. So you can copy this. Cameras off, please. You can copy this address down. Okay. I'm going to give you some time to copy it down, and then you can copy these questions down as well. What happens when you held the nail over the paper clip? Why were the paper clips attracted to the nail? And does the disconnected nail attract the paper clips, and why? So when you disconnected the nail or you put the switch off, did it attract the paper clips or the iron fillings? And then give a reason why. So I'm going to give you a minute to take the website down, because when you actually look at something happening, it makes it a lot easier for you to understand. So take the website address down, and then take the questions down, and then you can answer those questions as your homework. You have 1 minute. Okay, so now let's summarize what we've learned so far. You've learned that a current causes a magnetic field, such as an electromagnet. So now, when you know that when a current causes a magnetic field, it is called an electromagnet. An electric current can be used for making temporary magnets. So you also know that an electromagnet is a temporary magnet. And then we have moving charges, which is the current in a conductor, such as a wire, causes a magnetic field around it. So moving charges causes a magnetic field around it. Then you also learned that an electromagnet is a type of magnet in which the magnetic field is produced by electric current. And electromagnets usually consist of wire wound into a coil. So now you know that that wire is wound in a coil, and we need that length because that length gives you more current to go through it. And the current through the wire creates a magnetic field which is concentrated in the hole, which is at the center. Levi, you have a question?
Just one more thing, part of the summary, please.
Yes.
An electromagnet is made up of a core of soft iron and a coil, and it's also made up of a coil of insulated copper wire that surrounds the iron core. The coil is called a solenoid.
Okay, very good. Well done to you. Okay, so now that coil he added is called a solenoid. Okay, so you learned a new wire. You want to repeat that again, Levi, so that everybody can hear?
Yes.
Okay.
An electromagnet is made up of a core of soft iron and is also made up of a coil of insulated copper wire that surrounds the iron core. The coil is also called a solenoid. Just read
Okay,
it
well,
from my textbook.
yeah, I know. Well done. I'm very happy. You know what? By the fact that you're listening to this lesson and then you're looking through your textbook shows you that you're a keen learner because you're actually taking what I'm learning, you're looking at the pictures and you're consolidating it means that you're putting it into perspective because you're understanding it better. So well done for that. So
Thank
let's
you.
do that from tomorrow, everyone. When we're doing this lesson, our lesson tomorrow, we're going to talk about electricity in chemicals. Take your textbooks out, and it will help you to learn better. Well done for that idea, Levi.
Thank you.
You are welcome. Okay, so now all the information that I derived from this was from ciuvela.com, and the Department of Education uses this website to make their own workbooks as well. And then I also got information from Education Resources High School on magnetism. And if you want, you can watch this YouTube address here. You can copy it down. How the magnetic field protects us from the damaging sun's rays. So it's very nice for you to know that how magnetic field protects us from the sun rays. So take this website down. It's YouTube y youtu.be capital letter MZ, small letter T, capital letter TV, small letter S, capital letter IOA, number 9, small letter C. Because you need to know that you live in an environment and you must know how that the magnetic field around us is basically protecting us. And then the other website I gave you to copy down was basically this address here. Is basically how to make an electromagnet. Right, it's been a pleasure tutoring you today. I enjoyed my lesson. I hope you benefited from it. So tomorrow we're going to discuss chemical effects. with electric current. And my email, if you want to contact me, ahaffea@gmail.com. Thank you for joining me. See you tomorrow and have a lovely day. Goodbye, everybody.